right. Well, my name's Heston Bryant. I'm with the thermal analysis side of the flight analysis division of NASA's Launch Services programs at Kennedy Space Center. We're hosting the Thermal Fluid Analysis Workshop this year virtually. And here today we have Derek and Jacob of Redwire, and they're here to present Veritrek, which is a reduced order modeling thermal software that works with Thermal Desktop to make challenges more manageable. And they have quite a list of use cases here to show today. And I think you guys can go ahead and take it away.
All right. Thanks, Heston. And thanks, everybody, for joining. Heston, I really like that, how you put it, make challenges more manageable. So we're here to talk about Veritrek. And as Heston had mentioned, essentially Veritrek is a companion tool to Thermal Desktop. So hopefully you're Thermal Desktop users in the audience. And if you are, this is the right place to be. Veritrek is a tool that basically plugs into Thermal Desktop and allows you to convert Thermal Desktop models, high fidelity Thermal Desktop models, into a reduced order form. The reason that you might want to do that is whereas a Thermal Desktop model might take minutes to hours to days to run a single simulation, by converting that into a reduced order model using Veritrek, we can now run thousands of those simulations in a few seconds. So that's kind of the big take home here is that Veritrek is a reduced order modeling software tool for Thermal Desktop. We've got a number of folks that are using Veritrek for a pretty broad range of different applications. Those are shown on this first slide. We did some work with NASA JPL on their Mars 2020 helicopter program. We looked at sensitivities of that thermal design using Veritrek, identified kind of problematic areas to help them better optimize their thermal design. We also use Veritrek as a mission ops tool. So once the helicopter was on Mars, they used our reduced order modeling tools, again, leveraging the speed of a reduced order model to help with mission planning. We have NASA Marshall Space Flight Center. They've used Veritrek for their lunar lander program, basically using Veritrek to develop response surfaces, to better interrogate and investigate their thermal design. NASA Goddard used Veritrek looking at design sensitivities on their Exclaim program. And then also NASA Goddard used Veritrek for model correlation. Veritrek has, as we'll see later, Veritrek has a rapid thermal model correlation tool. They use that on their LRALPH program. On the bottom row here, again, some commercial customers, ATA Engineering, used Veritrek for a design optimization for a CubeSat. Sierra Space used Veritrek on their Dream Chaser program. Ball Aerospace used it for, again, rapid thermal model correlation. And then Momentus recently used it for risk mitigation on their Vigoride 2.1. So just kind of a sampling of customers using Veritrek, using reduced order modeling for their thermal analysis. With that, I'm going to jump into some more, I guess, high-level details of what Veritrek is, how it works. Before we get into that, though, I do want to mention, if you have any questions at any point, please put those in chat. This is a pretty informal conversation. We want to understand what you're interested in, what your questions are, so feel free to interrupt us at any point. All right, so what is Veritrek? We've already talked about it. It converts thermal desktop models into a reduced order form. The question is, how does it do that? We kind of break it down into a three-step process. So step one is you start with your thermal desktop model. Really, the only restriction we have here is that it has to be thermal desktop 6.0 or greater, so we can take advantage of their OpenTD API. And so that's kind of the limitation. If it's a predate 6.0, we won't be able to work with that, but I think there's ways around that by upgrading your model. As far as the fidelity of your model, it can be high fidelity. It can include a fluid system. There's also pretty much anything that's been thrown at Veritrek we've been able to handle. Once we have your thermal desktop model available, we then take our Veritrek creation tool, which basically puts its hooks using that API into your thermal desktop model. And it allows you as a user to semi-automatically convert that thermal desktop model, your thermal desktop model, into a reduced order form. At the end of step two, the end of the creation tool, you then have a reduced order model. And really, if you look at it, it's really nothing more than a set of coefficients. And it's really hard to make sense of it. So we do need another tool to be able to read that reduced order model and make use of it. And that's where the exploration tool comes into play. The exploration tool reads that reduced order model and then gives you the ability to take advantage of the speed of a reduced order model. Again, thousands of results in seconds. And I think we're going to play a quick video here to kind of show you, at the end of the day, what all of this looks like. So this is a video of the exploration tool. Prior to this, we took the thermal desktop model, which happened to be a simplified NASA crew exploration vehicle thermal model. We ported that or converted that into a reduced order form and pulled that into the exploration tool. This particular thermal desktop model had a fluid system on it. It had a regenerator, had radiators, had heat loads. And so what we see in the middle of this video are the input factors to our reduced order model. We see things like different working fluids. You see that up at the top. We see space temperatures. We can change that value. We can change the radiator emissivity or fin efficiency. We can change heat loads. So, typical culprits that we see in thermal desktop. But every time the user is changing one of those input factors, you can see that the user's clicking on those sliders. We see the result of those changes on the right-hand side. And on the right-hand side, we're showing our response surface plot, basically a 3D plotting feature that shows a single output response, which in this case is fluid hydraulic power, as a function of two of these inputs. And really what's going on behind the scenes is that every time the user is moving one of those sliders, we're running 400 reduced order model simulations in the background to generate this response surface. And you can see that's happening in basically in near real time. And you can imagine using traditional approaches, it's just typically too computationally expensive to do that. Just imagine running 400 simulations in thermal desktop to generate the data, taking that data to then generate a response surface. I mean, that's pretty computationally expensive to do that. But by first converting our thermal desktop model into a reduced order form, we can do that again in near real time. All right, we can go to the next slide. So hopefully you're starting to think about, why would Veritrek be useful? Again, we have thermal desktop. I'm a daily thermal desktop user. It's a powerful tool. Typically my simulations are minutes to hours per simulation. Usually I'm left, running worst case analyses, kind of the corner cases or the bounding cases. But with Veritrek, by converting our thermal desktop model into a reduced order form, we can then take advantage of thousands of simulations in seconds. And that really opens up the type of analyses that we can do. We can do things like response surfaces, which we see a picture of that here in the middle. Going from the bottom left up to the upper right, these are all different analysis types that are included in Veritrek. The bottom left is basically an Excel plotter or an Excel-like table. We also have uncertainty quantification, which is shown there next. We have a 2D plotting feature. Again, the 3D plotting feature. We have our thermal model correlation analysis tool. We have screening analyses or sensitivity studies that we can do with Veritrek. And then at the upper right, we can take advantage of the speed and we can basically throw thousands of results to do optimization. All right, so we can move on to the next slide. We often get the question, well, what is a reduced order model? I've talked about we're converting our thermal desktop model into a reduced order form. I also mentioned that the reduced order model is a set of coefficients. So really, what is a ROM? And so this is a very simple example of what a reduced order model is in the eyes of Veritrek. So in some cases, folks might convert high fidelity models into low fidelity and call that model reduction. That's not what we're doing. We're essentially sampling our thermal desktop model, and then we're doing robust data fitting on that sampled information. And so we have a very simple example here. So imagine you have a thermal desktop model, and let's say we have an input factor of, let's say, a heat load on a component, and that's on our x-axis. And we're going to vary our heat load from 0 all the way up to 5 watts. And what we want to understand is what is the impact of changing that input factor. So what's the temperature of a node as our output response. And so we're going to sample our design space by running our thermal desktop model at 0, 1, 2, all the way up to 5 watts. And then we're going to, at each of those settings, we're going to track the temperature response. And we basically generate these this data that we see here, these red circles. And so the next logical step might be, well, this looks pretty linear. Let's do a data fit on these circles. And so we do that. We generate a equation y equals 10x plus 10, pretty straightforward to do that process. And then let's say someone came back and they said, well, what's the output response, or what's the temperature of our node of interest at an input setting of 3.5 watts? Well, we haven't sampled that before, and we certainly could go back to the thermal desktop model and rerun it at 3.5 watts, and we could get an output response of 45. But a more efficient, more computationally efficient way is to use this model that we've already generated. Put in 3.5 in for X, and out comes 45 for our output response. And that's essentially what we're doing with Veritrek. We're sampling, so determining the points that we want to sample across our input design space. We're generating this data. We call that training data. And then we're generating a data fit of that training data to generate this model. And with Veritrek, we're really expanding quite a bit beyond this very simple example. We provide this simple example because it's 2D and we can show it on a PowerPoint slide, but Veritrek's really going pretty far above and beyond what we're showing here. We're not just dealing with a single input factor with reduced order models. We're dealing with multiple input factors. The most input factors to date is that we've had a customer use is 33. We're also dealing with multiple output responses. So not just a single temperature output response, but multiple output responses and not just temperature. We can certainly track temperatures, but we can basically anything that you can assign to a register, we can track that as an output response. And the most output responses a customer has included in the reduced order model is 91 to date. So kind of giving you an idea of the number of inputs and outputs for our reduced order models. The other thing that Veritrek does and does quite well is sample the design space. You can imagine that the expense of doing this are running the simulations to generate the training data. And so our sampling scheme, we have a highly optimized sampling scheme that gives you enough sampling points, but no more than what's needed. And we'll certainly talk about that later on. And also we have a very robust data fitting algorithm in Veritrek. You can imagine with thermal systems, they're not going to be nice and linear like this simple example. Thermal systems are highly nonlinear, especially with space thermal, with the radiative effects, kind of that temperature to the fourth effect. And so Veritrek's data fitting methods can handle those highly nonlinear systems. All right, we'll go to the next slide. All right, so when can you use Veritrek? We certainly thought early when we were developing this tool, this software tool, that Veritrek would be great early in the design stage. You're dealing with multiple options that you're trying to decide between. Are you going to go active or passive? How big is your radiator going to be? What kind of optical coatings are you going to use? Things like that. We thought it would be great as an early design trade study tool, and that's certainly held true to this day. An example is some of the work with NASA Goddard with their Exclaim program. But as we've worked with customers, we've really found that Veritrek is being used throughout the design life cycle, whether it's early design trade studies, maybe when you have a detailed design, trying to understand the sensitivities of thermal inputs and how they impact outputs. Example is some of the work that we did with NASA JPL on their Mars 2020 program. We also had ATA engineering that used Veritrek during the detailed design stage to optimize their thermal design. In that particular example, they had multiple radiators and they were trying to trade radiator size and trying to make sure that the size met both hot and cold case conditions. Also with final design activities, we had Momentous that used Veritrek for a final design verification, really trying to make sure that their design was going to work in a broad range of different scenarios. And then also towards the end of the thermal design life cycle, we've had a number of folks using Veritrek for model correlation. So even going past your traditional thermal desktop model, now you're porting that into a TVAC model, and you have physical hardware, and you're trying to correlate your TVAC temperature sensors to your TVAC thermal model. And so we've had a number of folks use it there too. So really, I think the answer here is that Veritrek's really being used throughout the entirety of a design life. All right, and with that, I'm going to turn it over to Jake to go through some demos to kind of show you how Veritrek works. Again, I just want to mention, if you have any questions or you want us to stop and cover something in more detail, please let us know through chat.
Yep, thanks, Derek. Okay, so the next little bit of this presentation, like Derek mentioned, I'm going to take a step further into kind of what the software actually looks like and how it works by talking about both how to build a reduced order model in the Veritrek creation tool, but then how we use that reduced order model in the Veritrek exploration tool. So I'll start by talking about how we build a reduced order model inside of the Veritrek creation tool. It's a pretty straightforward and hopefully easy process from the user perspective. The first thing that Veritrek is going to do is it's going to import your thermal desktop model. So you choose the .dwg file that you're going to build your ROM from. And Veritrek, using Thermal Desktop's OpenTD API, will go ahead and import all of the necessary thermal model characteristics that we need to build our ROM. So that's going to be symbols, registers, nodes, K-sets, etc. All of that will get imported into Veritrek. From those thermal model characteristics, the user will go ahead and set up their ROM. So you'll choose, which symbols you want to use as input factors, which nodes or node groups or registers you want to use as output responses. And we'll see that in the video here in just a minute. Once a user sets up their inputs and outputs, Veritrek takes over in a semi-automated fashion. So the sampling and data fitting algorithms within Veritrek will take over to generate the sampling points, run each of those sampling points through Thermal Desktop so that we generate our training data, and then perform a fit on that data so that we end up with our end of the day fully created reduced order model. And so that kind of completes the ROM creation step. There is one last little bit inside of the Veritrek creation tool. That's our ROM testing step. So once we have our fully created ROM, we can actually do some testing on that ROM with a unique set of thermal desktop model runs to kind of compare ROM prediction results to actual thermal desktop model results. So we provide the user with a sense of how accurate the ROM is performing and allow a user to make a decision on if you want to improve the ROM accuracy or if you're fine using it in the exploration tool with how accurate it is at that current point in time. So now I'm going to bring up a video that just kind of shows myself going through the Veritrek creation tool workflow. So I'll be talking over it live with you guys here.
Hey, Jake.
Yes, yep.
Yeah, can we just pause right there? There was a question from Heston. Appreciate that. Are there limitations to data fitting such as sharp transient? That's a great question, Heston. Of all the data fitting models that we have to contend with, these sharp transients are probably the most challenging for us. We can certainly handle those, but you have to make sure that you're sampling quite a bit around those transients, around those basically like a step function. There is some work that we've done on that, and I'm happy to point that out to you if you want, but that's probably our most challenging situation or scenario that we contend with. And kind of the take home is we can do it, but we have to be careful around that transient location and make sure that we're sampling fairly densely at that location to capture it.
Yes. I was wondering if there was that sort of automatic implementation of that sampling increase, but it sounds like you've ran into
great question. We don't have automatic implementation of that as of right now, but it's something that you can in the creation tool. You can manually set sampling points, so you kind of want to make sure that you more densely sample that around those transients.
Makes sense. Yeah, I think engineers can do that. Yes. Sorry, I'll let you get back to it.
Yeah. Yep. Thanks.
Mhm.
Great question.
Yeah, thanks for that question. Okay, so just going to show a video here that shows the creation tool workflow. We're just starting off in Thermal Desktop, kind of showing the demo model that we're going to build our ROM from. So this is just a generic 6U CubeSat. You can see the different components that we have, isothermal components that we have broken into different submodels or node groups. We can take a look through our symbols deck. We have some registers tracking some unique output responses that we'll use. And then we have a couple of case sets as well that are just using some thermophysical property overrides to control the material of this CubeSat's radiator. So just setting a little bit of context. Now we'll go ahead and open up the Veritrek creation tool. The first thing we're going to do is give our ROM a name, and then choose that .dwg file that we're going to build our ROM from. We'll choose a save location for our ROM, and Veritrek for the first time will open up our thermal desktop model and import those necessary thermal model characteristics that we need to build our ROM. So now we can move on to the Inputs tab. The area in the top left exactly mirrors our thermal desktop symbols deck. So you can see those different tabs with the symbols underneath each one of the tabs. And all a user needs to do here is select the symbol that they want to include as an input factor. They select that symbol on the left. It shows up in this table on the right. And this table on the right is where a user is defining the design space range they want to investigate with their ROM. So the user specifies a minimum and a maximum symbol value, as well as how you want to look at that symbol from the minimum to the maximum. You can look at it in a continuous fashion or discrete values. And then we'll add the case sets that we want included within our ROM as well. Next, we're going to do the same thing for our output responses. So all of our thermal desktop model nodes show up on the left. Registers and node groups show up on the left as well. And we simply select those output responses we want to include on the left. They show up in this table on the right. And this table on the right, I'll actually pause it here because since we had a question on kind of transient output responses, just want to specify or clarify what's going on here. So once you select an output response on the left, again, it shows up in this list on the right. For transient simulations, what Veritrek can do, you can choose to track the minimum, mean, and or maximum, either individual node temperature, register value, or entire node group temperature throughout that transient simulation. So we're really kind of pulling out those inflection points or kind of the minimum or the maximum value of that output throughout the transient simulation. If your case set in your thermal desktop model was a steady state run, it wouldn't matter which of these options you would select. They would all be the same. So the minimum, mean, and or maximum, and we actually have max gradient temperature now. Those are for transient simulations specifically, and you're specifying here which of those values you want to pull out of that transient simulation. And we do that for temperature and registers as well. So now that the user specified the inputs and the outputs, this is where Veritrek's going to take over in a semi-automated fashion. So we'll move on to the ROM setup and summary tab. The bottom of this tab just provides a summary of the inputs and outputs we've selected. The area in the top left, I won't get into all of those details here. We provide those in the user manual, and if questions come up, I can certainly address them. But this is where Veritrek is telling you the number of training runs or sampling points to use for this particular ROM. You can come in here and change the default value, but typically the default value Veritrek provides is a good place to start. We can see those different training runs that need to be performed in Thermal Desktop show up in this ROM Creation Status tab. Here, the user just needs to click Start ROM Creation. Veritrek takes over. It passes each one of these training runs off to Thermal Desktop, where that run gets performed in its entirety. Veritrek goes into that run save file, pulls out the necessary output information we need, and that gets stored as a single training data point. And that process will repeat until all of the training runs are performed and we have our entire training data set, at which point the user will just click Generate Fit, and Veritrek will run that training data through our data fitting algorithm in the background. So now we have a fully created ROM. Like I mentioned before, we're going to test that ROM. And so we're going to generate a unique set of thermal desktop model runs that we'll use as our test data. That test data will get generated in thermal desktop in a similar fashion to the training data that we use for the ROM itself. Once those test runs are performed in thermal desktop, what we can do, we have these plots, these testing plots, along with numerical data to compare ROM prediction results to measured thermal desktop model results. So we have these plots, one for each output response. The red circles are our test data points, and the green diagonal dashed line represents an ideal or perfect ROM fit of our underlying thermal desktop model. So you can see in some cases, we're not going to be perfectly along that ideal line. Using those plots along with the numerical test data in the form of mean of the residual and standard deviation of the residual, it's really going to be up to the user at this point in time, how accurate you need or want your ROM to be. If it's, what you're seeing right now is accurate enough, you can go ahead and port it into the exploration tool, which we'll show in just a minute or two. If you're not comfortable with how the ROM is performing, if there's one or two output responses that are not very accurate, you can come into our optional ROM improvement tab, essentially just generate more thermal desktop model training runs, add those to your already existing ROM and kind of improve the ROM accuracy in an iterative manner. Typically 3 to 5 degrees C or 3 to 5 Kelvin is what most people kind of shoot for standard deviation of the residual, and we can get 1 to 3 degrees C or 1 to 3 Kelvin per mean of the residual without too much difficulty. But again, we have had some people that have used Veritrek for cryo-type applications, and so they need to be much more accurate than that, and we can certainly get there. It just takes a little bit longer to create the ROM because we need more training data to improve that ROM accuracy. Okay, I'm going to jump back into the slides. And now we can talk about how to use a ROM.
Hey, Jake.
Yes.
Yeah, I just want to pause you right there. There's another question that came in that I think was kind of timely. Does Veritrek reuse radiation calculations, if applicable, between training runs?
Yeah, that's a great question. And so the short answer is yes. That's a new feature that we rolled out with Veritrek 4.2, and so we'll talk a little bit about that here in a couple of slides. What we can do there is allow a user to kind of group or sort together training runs that will reuse radiation calculations. So we can kind of intelligently order the training runs so that we can take advantage of that. But that is a new feature. That's a good question. Okay, so now let's talk about the exploration tool. Once a reduced order model is fully created in the creation tool, you've tested it, you're comfortable with how it's performing. It's a pretty simple process to go ahead and import that into the exploration tool and use any of the 7 analysis features that we provide to perform your rapid thermal analysis. And we'll go ahead and show a video of that here. So we're going to open up the Veritrek exploration tool. The first thing we're going to do is import a new ROM. So we're going to import the ROM that we just created and tested. Once we import that new ROM, we're going to start a new exploration tool analysis session. We'll give our session a name, and we'll tie that session to a particular ROM. So the ROM that we just created and imported shows up in our list of available ROMs. And now we're off and running. We can use any of these analysis features to perform our rapid thermal analysis. So the rest of this video is just going to provide a quick highlight of these analysis features that Derek mentioned earlier. This first one is our point analysis feature. It's an Excel-like table that you can use to evaluate discrete point designs. So you'll notice output responses on the right-hand side are changing in real time as we make adjustments to our input factors or thermal desktop symbols on the left-hand side. Next is our 2D factor sweep analysis. So this is a parametric sweep plotter. We're sweeping through a range of values for one input parameter on the x-axis and looking at how an output response on the y-axis changes as we sweep across that particular input. And we can certainly make adjustments to other input variable values on the left-hand side and see how our parametric sweep plot changes. Our surface plot analysis feature that we looked at a little while ago is simply an extension of that 2D parametric sweep plotter, although instead of sweeping through a range of values for one input on the x-axis, we're doing it with a second input on the y-axis as well, and looking at how our output response on the z-axis changes. So we end up with this 3D response surface, which we can certainly zoom in, zoom out, rotate this around. There's a top-down kind of contour map view of this as well. Next, we're going to look at our screening analysis feature. So a lot of people use this for sensitivity studies. What's being plotted here are Pareto bar graphs. And so the larger the bar graph, the more of an impact on average that particular input parameter has on our output response of interest. So all of our input parameters show up on the x-axis. And again, the larger the bar graph, the more of an impact on average that input has on our output. And so you can kind of very quickly, qualitatively and quantitatively observe those thermal design drivers, understand which inputs are really driving your output responses of interest. Next, we're going to look at our optimization analysis feature. So this one is a little unique or different as well. We're actually looking at two output responses on the x and y axis. We're going to generate Pareto front plots to really understand kind of the bounds of our thermal design and perform a design comparison in this example. So I'm setting up two different runs here. One that's leveraging kind of nominal standard thermal control hardware for our 6U CubeSat. A second design option that's leveraging some advanced thermal control hardware. We're very quickly going to interrogate each of these two design options with thousands of data points, and we can very quickly, visualize and observe that using the advanced thermal control technology, we can help reduce the maximum temperature of our satellite's payload by about 15 degrees C in this example. And our correlation analysis feature. So I'll actually talk about our two newest analysis features in a couple of slides. This is one of them, our rapid model correlation feature. This was really geared towards assisting thermal teams correlate their thermal desktop models to thermal balance test data that they receive in the lab. What we do here is ideally we have nodes in our thermal desktop model that correspond to thermocouple locations from our TVAC or thermal balance test. So all we're doing here is specifying, we're telling Veritrek what we want those node temperatures to be. And again, those come from thermocouple readings from our test. And what Veritrek is going to do is it's going to interrogate our design space and come up with combinations of input parameters that yield these particular output responses that we've specified. And so all of the available combinations that Veritrek finds from the thousands, tens of thousands, in some cases we've had users explore millions of different combinations of input parameter values. Veritrek will investigate all of that, kind of sort and filter it out, and provide you with a list of viable combinations that effectively correlate your thermal model. And our latest analysis feature is uncertainty quantification, which I'll talk about here in just a couple slides. So getting into kind of the new features with Veritrek, I know some folks on this call, you may have heard us talk about Veritrek before or seen some of the different things customers or users are doing, but we just wanted to highlight, the large amount of progress we've made in the last year or year and a half. So these are kind of in case you missed it slides with the latest versions of Veritrek. Veritrek 4.0 came out kind of the middle of 2021, so a little over a year ago. And this brought with it two new features that we've been excited to have users use over the last year. One is on the ROM creation side, and that's a ROM parallelization feature. So we certainly, hopefully from the discussion that we've had today, we certainly don't want to hide away from the fact that we recognize the biggest investment or ask from a user perspective to utilize Veritrek is the initial time investment that it takes to create a reduced order model. Since our reduced order model is generated with actual thermal desktop model runs, the larger your ROM is, or the longer it takes your thermal desktop model to complete one run, the longer it's going to take to build an accurate ROM that you can use. And so a lot of our development and kind of focus is geared towards mitigating or reducing that cost as much as we can. And that's what this ROM parallelization feature was really geared towards. It's to help reduce the time that it takes to create the reduced order model. And so what you can do now as of Veritrek 4.0 is split the training data into multiple batch files. And the caveat being, if you have multiple thermal desktop licenses that are available, you can actually generate your training data in parallel. So you can open up multiple instances of the creation tool, let Veritrek create that training data in parallel with multiple thermal desktop licenses, merge that training data back together, perform the data fit on the entire training data set, and kind of help speed up the ROM creation process. And then the model correlation feature that I was just kind of talking about, this is a little over a year old now as well. This is just another video kind of showing how this feature works. We're actually going to correlate to 2 thermal balance tests in this demo video. We've had folks correlate up to 8 thermal balance tests at the same time. Typically, people are doing, between 2 and 3. But again, how this feature works, you're specifying or you're telling Veritrek what you want, your node temperatures to be. And what you want it to be comes from your thermocouple readings from your thermal balance test. So you're specifying what you want those output response values to be. You can tell Veritrek, how far off of these values you're willing to accept. Here at Redwire, we typically go plus or minus 3 degrees C for our model correlation. So we're specifying a margin criteria here in the margin column. Since we're correlating to 2 tests at the same time, the first one was our cold test, the second one is our hot test. We're again just specifying the output response values that we want Veritrek to find input combinations for. And once we do that, we just tell Veritrek how many points down here we want it to investigate. In this example, we're doing 20,000. So Veritrek is running through 20,000 different combinations of input parameter values, looking at the correlation criteria that we specified, and it's going to sort and filter out those that meet our correlation criteria. And the end result is this table on the right, which shows us the list of viable combinations. In this example, since we're correlating to 2 thermal tests at the same time, each solution is really grouped into a row of 2. And so you can see our input parameters here in the center portion. You can see the different combinations that Veritrek found that meet our correlation goals and criteria. Let's see, Veritrek 4.1 kind of came out at the end of 2021, early 2022. This was a smaller release with the release of Thermal Desktop 6.2. We just wanted to make sure that the latest version of Veritrek worked well with the updates that CR Tech made to the OpenTD API. And so that compatibility with Thermal Desktop 6.2 was included. And then we also added in a max temperature gradient output response option for node groups. So now in the creation tool, when you specify what you want your output response to be, there's a max gradient option that's here as well. So you don't have to set that up as a register to track it. And then our most recent release in Veritrek 4.2, this is actually a release that occurred this summer, so about 2 months ago, a little over 2 months old now. This was another big release for us. It brought with it a new analysis feature inside of the exploration tool, and that's our uncertainty quantification analysis feature, which allows you to help make statistically based conclusions about the uncertainty of your thermal model or your thermal design. So in some cases, we may have symbols or input parameters to our thermal desktop model that have some uncertainty as to what their actual value will be. If we're getting the variable values from a handbook, maybe there's beginning of life, end of life situations with our input parameters. There's some uncertainty within our thermal inputs, and we want to understand how that uncertainty propagates to our output responses. And that's what this new analysis feature allows us to kind of visualize and understand. And so the plot, looks, functions, works like our other analysis features. What we're looking at here is actually an output response on the x-axis and frequency or kind of likelihood of that output response value occurring being on the y-axis. And so we're able to generate these histogram plots. Veritrek, using the power of the reduced order model, again, kind of interrogates the design space available to it with the reduced order model. You can explore tens of thousands, hundreds of thousands of points, and it'll track the different output response values that it finds for the inputs given their uncertain range that you specify. And we end up with these histogram plots that show the statistically significant most likely value or statistically significant trend for that output response. Within Veritrek 4.2, there were also some new creation tool updates as well. So I kind of mentioned the smart ordering of training runs feature earlier on. This is if you know if one of your inputs is going to be like maybe an optical property, the ray tracing, the RAD-K calculations are going to be the same. What you can do is simply sort or group runs together that are going to have that same value. And so you can simply right click here in the ROM creation status tab. You can do a multi-column sort, and then you can choose which input parameters you want to sort by. So it's not fully automated yet. Veritrek can't go in and recognize which particular runs might be able to reuse RAD-K or ray tracing, but you can kind of do a manual group if you know ahead of time that you want to do that. And that can help save ROM creation time as well. And then we've also updated some of our ROM testing plots and information that we provide there. And then we've provided a data fitting time tracker or time estimator so that both in the training data generation and the training data fit how long Veritrek needs to work before your ROM is complete. Okay, yeah, so now the next couple of slides, we'll just kind of quickly highlight some case studies, some user success stories that we've had. I think, Derek, I'll take the first couple here and then let you kind of finish things off. This first one, ATA Engineering has used Veritrek to perform some radiator size optimization for a 6U small-sat bus model that they were working with. So they actually had 6 different body-mounted radiators on 5 different sides of this bus and wanted to optimize the size of each of those 6 radiators based on temperature requirements in hot conditions and then heater energy requirements in cold conditions. And so they were able to use Veritrek's optimization and point analysis features to sort of optimize each of those 6 geometries and filter down to a single optimized design solution. Momentus has used Veritrek to perform some design risk mitigation and also to do some kind of future mission operation trade studies. And so they've used this at kind of the CDR level of their thermal design and a little bit more forward looking on the mission ops side as well. So they used Veritrek's 2D parametric sweep or factor sweep analysis to kind of look at multiple design options and choose a best design solution based on multiple output response requirements and types, heater power and max battery temperature in this example. And then doing some trades on different ConOps leverage. So these 2 design comparisons that they did, they were looking at maximum temperature of an onboard component and trying to determine how beneficial it would be if they leveraged some thermal energy storage on board, how much more, ConOps or actual operation of their space vehicle could they do if they could keep that component temperature low enough. And so being able to do kind of a direct one-for-one design comparison gave them some insight and information that helped plan future space vehicle design and mission operation parameters. Okay, Derek, I'll turn it back over to you to talk about the last few case studies and then kind of close things out.
Yeah, thanks, Jake. I'm sorry, I'm reading the questions. We have a question. Can you correlate over the entire transient run? That's a great question. It kind of opens a pretty broad area of discussion for us. So when we're generating reduced order models, we can generate reduced order models for steady state and transient runs. For the transient runs, we basically pick inflection points, maximum temperature, minimum temperature, and average temperature, for example. Providing a reduced order model to replicate the full transient profile, so temperature versus time, is not something that we currently do, but it's something that we've actually spent quite a bit of time looking at. So to answer your question regarding correlation, we currently don't correlate the transient run. We basically correlate, balance temperatures, for example. Hopefully that answered your question. Let's see, there's 2 other questions. Examples have shown thermal only models. Is this also compatible with fluid or mixed thermal fluid models? Just the same? Yeah, absolutely. If you recall, the very first video that we saw from the NASA Crew Exploration Vehicle, that was actually a thermal fluid system. So it had, thermal radiators, but it had a pump fluid system going through those radiators that had different working fluids. So certainly can handle both thermal and also thermal fluid thermal desktop models. All right, another question. These are all great, so I appreciate it. Can the ROM be extracted and run independently? Yeah, so could we basically take the reduced order model, and if I read this correctly, and I haven't read all of the question, but can we take the ROM and instead of using the exploration tool, can we circumvent that and allow users to access that reduced order model independently? Currently, no, but we have had conversations with customers about that capability. We're kind of thinking about the impact of that and how best to approach it. If you do have an interest in that, I'd love to talk more about that in the future. Sorry, I'm just going to read through the rest of this question here. Bear with me. Yeah, I think hopefully I answered your question, Michael, but yeah, really appreciate the questions and feel free to stick around if you want to do a deeper dive into that. I know we have a couple minutes left. I want to get through the next couple case studies, kind of wrap things up, and then we'll leave a few minutes at the end for other questions. So again, appreciate all the questions. These are great. All right, so this slide and the next one really talk about the Mars 2020 program and how we interacted with them. We first got involved with NASA JPL. This was earlier in the program. They had a fairly mature thermal model, thermal design, but they were trying to optimize that design and try to really what they were getting down to is trying to minimize the required survival energy during the cold Martian night. And so they're trying to understand what thermal inputs, think of like conductances, or they had a number of gas gaps and convection parameters, which of those were impacting the survival energy the most. And so we used our screening analysis to do that. We see that in the lower left. And so by using the screening analysis, it was pretty clear that there was a couple kind of primary culprits that were impacting that survival energy. Again, survival energy is on the y-axis, and then the different inputs are on the x. And so that was one way that they use Veritrek. They also use Veritrek as a check of their design. How well does it meet the temperature requirements? And so we used our optimization analysis, basically using a Monte Carlo approach, throwing thousands of simulations at it. Do any of those simulations basically fall in the keep out zone, which this is a preliminary run that shows that, yeah, some of these points do fall in the keep out zone. And so from this information, they use that, they hovered over these points, or more thoroughly investigated these keep out points and understood what was driving that. And then that allowed them to tighten up their design a bit. Yeah, Jake, we can go to the next slide. And so we did some follow-on work with NASA JPL, again, on their Mars 2020 helicopter. We basically, as I mentioned earlier, we basically developed a pretty high fidelity reduced order model for mission ops. There was a very limited time window for them to get telemetry from Mars and turn that around in terms of a plan for how to operate the helicopter for the next mission. And because of that, they wanted to leverage reduced order models to help them do a number of things. One is to help better correlate their thermal model based on the telemetry that they're receiving. And then also for mission planning, how do they operate the warm-up heaters to get their helicopter to a warm enough state to run? And so that's how this ROM was developed. This ROM, it was fun because we had a lot of calendar time to develop the ROM. So we just threw a lot of training points at it. 3,600 training data points at this thing to get a really nice fit of ROM prediction versus the thermal desktop truth results. All right, Jake, next slide. All right, here's an example of some of the thermal model correlation work that we did. This is with Ball Aerospace. So they had a cryogenic instrument and they wanted to do some thermal model correlation. They took that cryo instrument, they ended up breaking it down into 3 separate thermal models, and then they used Veritrek to correlate those 3 thermal models. For each of those thermal models, they used 20,000 ROM iterations that produced a collection of solutions. So roughly 4,000 to 5,000 solutions that met the plus or minus 1K requirement across 10 different test cases. And so, they use this to successfully correlate those 3 different thermal models. This is an effort that typically would take them 3 or 4 weeks, and using Veritrek, it took 1 or 2 days. So, pretty significant reduction in the amount of time to get this stuff done. All right, next slide. Yeah, so this is our last slide, and yeah, this will leave us about 5 minutes for questions. If you're at all interested, we do have a free trial that we can get in your hands. Again, this needs to be used with Thermal Desktop 6.0 or greater. If you do have any interest, whether if you want to get a free trial or if you just want to talk further, we're more than happy to talk about your applications and to see if Veritrek can help you out. Feel free to reach out to Jacob. His email is here on this slide, or myself. I'm sure my email credentials are out there somewhere. or you can just reach out to us in the chat here. But I really appreciate everybody's attention. If you do have follow-on questions, feel free to type those in the chat. We're happy to answer those, and we'll be here through the top of the hour.
All right, thanks, guys. That was really great. I think the power in the use is pretty evident there, and I know we're interested in it, at least on our NASA side, and I'm sure many people are as well. Yeah, thank you for your time. That was really excellent. Really cool stuff
Great,
to see.
Yeah, appreciate the opportunity, Heston.
Absolutely.
Yeah, thanks, Heston. Thanks, Joseph.
Mm-hmm.